All right, welcome to this explainer. Today, we're tackling one of the absolute coolest puzzles in all of human engineering, how we actually make things move in the complete, empty vacuum of space. Down here on Earth, movement is pretty intuitive. We push against the ground to walk, our cars push against the road, airplanes push against the air. But out in space, there is absolutely nothing to push against. It's a total void. So how do aerospace engineers solve this ultimate physics problem? Let's dive in and find out. When we think of space travel, the Space Shuttle Discovery is usually what pops into our heads, right? Just this massive, earth-shaking launch filled with fire and smoke. It looks like pure, untamed power, ripping right through the atmosphere. But hook onto this thought for a second. While those massive launches look incredible, there's a highly specific, rigorous science to picking the exact right engine for every single mission. It's definitely not a one-size-fits-all situation. The engine that gets you off the ground is very rarely the engine you want keeping you moving deep into the solar system.
So, here is our roadmap for today's explainer. We'll start with the basics of space propulsion, then look at the two main engine families. Next, we'll dive into thermodynamic systems, follow that up with electrodynamic systems, and finally wrap up with choosing the right system.
Okay, Part 1, Basics of Space Propulsion.
So, what actually is a propulsion system? At its core, it's a complex machine that manages propellant, sensors, and controllers to give us a desired thrust. But here is the secret ingredient. And this is literally the biggest hurdle of spaceflight. It works by throwing mass backward. Because space is a vacuum, you have to bring your own mass with you, what we call the propellant, just so you have something to throw away. By forcefully checking that mass in one direction, your spacecraft gets pushed in the exact opposite direction. It's Newton's third law in its purest form. If you don't bring sacrificial mass to throw out the back, you simply aren't going anywhere.
Moving right along to Part 2, two main engine families.
If you look at the entire family tree of rocket engines, we can basically split them into two main branches: thermodynamic systems and electrodynamic systems. I honestly like to think of this comparison like a drag racer versus a highly efficient hybrid car. The thermodynamic branch, that's your drag racer. It relies on fiery, brute force heat and pressure to create this immediate, incredibly powerful thrust. It burns bright and fast. The electrodynamic branch, on the other hand, is our hybrid. It uses electricity to generate very slow but incredibly efficient movement over a really long period of time. One gives you a massive kick in the pants, while the other gives you a gentle, relentless push for months on end.
Let's look a little closer at the drag racers. Part 3, Thermodynamic Systems.
The crucial point of any thermodynamic system is heat. Whether you're mixing a fuel and an oxidizer in a classic chemical rocket to create an explosion, or you're using a giant solar concentrator to heat up a cavity, the fundamental principle is exactly the same. You are taking a propellant gas, heating it up so it expands rapidly, and then forcing it out of a converging-diverging nozzle to create thrust. Basically, the hotter the gas gets and the faster it escapes that nozzle, the harder it pushes the spacecraft forward.
Now, within this fiery thermodynamic family, chemical propulsion is by far the most common, and we subdivide it based on the physical state of the propellant. First up, we've got solid rockets. This is where the fuel and oxygen are pre-mixed into a solid binder. Just think of those huge white booster rockets strapped to the side of the space shuttle. Then we have liquid systems, which might use a single monopropellant like hydrazine, or a bipropellant mixing liquid fuel and liquid oxidizer, like liquid oxygen and liquid hydrogen. And sitting right there in the middle are hybrid systems, which actually combine a solid fuel with a liquid oxidizer to kind of get the best of both worlds.
But wait, chemical combustion isn't the only way to generate heat. Enter the nuclear thermal rocket. This is wild. Instead of setting fuel on fire, it uses an actual functioning nuclear reactor core to superheat hydrogen propellant before blasting it out of the nozzle. It completely represents the extreme high-energy end of the thermodynamic family tree. Because you're removing the need for a heavy oxidizer to burn the fuel, these nuclear systems can generate incredible thrust while being vastly more efficient than your traditional chemical rockets.
All right, shifting gears here. Part 4, Electrodynamic Systems.
When you see scientists testing electrostatic ion thrusters in these massive vacuum chambers, the sheer scale and complexity really becomes clear. Electrodynamic systems do not rely on heat and pressure. Instead, they require huge amounts of electrical power. We're talking kilowatts, usually gathered from massive arrays of solar panels. They use this raw electrical power, rather than fire, to accelerate charged particles to just staggering velocities out the back of the engine.
These systems come in a few flavors, primarily electrostatic, like xenon ion thrusters, and plasma systems, like Hall effect thrusters. The massive trade-off here? It's the thrust. Because they are throwing such tiny individual particles, Electrodynamic systems have extremely low thrust. Honestly, an ion thruster pushes a spacecraft with about the same amount of force as a single sheet of paper resting gently on the palm of your hand, no joke. But they do it with extremely high efficiency, reaching numbers well over 1,000 seconds of specific impulse. They can run continuously for months or even years, slowly but steadily building up incredible, mind-boggling speeds.
So how do we actually pick between the two? Part 5, choosing the right system. When engineers are evaluating propulsion, they always look at specific impulse, or ISP. You can think of ISP as the ultimate fuel economy metric for a rocket. A simple stored gas system, which is basically just venting compressed air, only gives you about 60 to 179 seconds of ISP. A solid rocket motor gets you 280 to 300 seconds, but when you move to an advanced cryogenic liquid bipropellant like liquid oxygen and liquid hydrogen, your efficiency jumps significantly to about 450 seconds. The type of propellant you choose absolutely dictates how efficiently you can maneuver out in space.
To define it formally, specific impulse is the ratio of total impulse to the mass of the propellant required to produce that impulse. Put simply, it essentially tells us exactly how much bang we get for our buck from the super heavy mass we had to drag all the way from Earth to orbit. The higher the ISP, the less propellant you need to pull off the exact same maneuver. And this is vital, because less propellant means you can dedicate way more weight to scientific instruments, crew supplies, or, just saving millions of dollars on launch costs.
And that efficiency directly feeds into arguably the most important equation in all of spaceflight, delta V. Delta V literally translates to change in velocity. It is the actual tangible currency we use to buy our way into different orbits. Whether you're trying to get to the moon, correct a satellite's orbit, or dodge a dangerous piece of space debris, everything has a delta V price tag. We calculate this budget by multiplying the engine's exhaust velocity by the natural log of the spacecraft's initial mass divided by its final mass.
Let's see how this plays out in a real-world scenario. Imagine the space shuttle is already in orbit. Its starting mass is 100,000 kilograms. It needs to maneuver, so it burns 1,000 kilograms of propellant, leaving it with a final mass of 99,000 kilograms. Step 1. We take the initial mass divided by the final mass and find a natural log of that ratio, which gives us about 0.0099. Step 2. We simply multiply that number by the engine's exhaust velocity, which in this case is 2,000 meters per second. And boom, there we have it. The shuttle achieved a delta V of 19.9 meters per second. The math perfectly predicts our maneuvering capabilities out there in the void.
Now that you understand the underlying concepts, the two main engine families, and the math that brings it all together, I want to leave you with a direct challenge right from the source data. Ready? A satellite needs an 8 meter per second orbit correction. Its thruster has an exhaust velocity of 800 meters per second, and the spacecraft's initial mass is 2,000 kilograms. By working the delta V equation backwards, can you run the numbers and calculate the exact mass of propellant needed for this maneuver? Take a moment, test your math, and see if you have what it takes to navigate the vacuum of space. Thanks so much for joining me on this explainer, and keep exploring.